Hello everyone and welcome to the second day of the Decision Science week. So I'm going to be here with you, and today we're going to see statistical inference. So what is a statistical inference? We're trying to guess the real value of something based on only a limited sample of observations, which means, for example, in our oldest case, we just have observations between 2016 and 2018, right? Um, we might want to generalize and see if the information and the statistical analysis that we're making through 2016 and 2018 would be accurate and robust on the future. So maybe in 2019, for example, if we didn't have the information. I guess today is 2021, but yeah, if you're trying to predict, how can you infer these observations from your sampling through the general data? So maybe if you take a sampling, also if you take a general population, let's say you want to measure the height of the average United States person, and you just take a few random people and just take the average of that random persons, how likely it is that the analysis, the average, the standard deviation that you take from that sampling can be generalized to the general population. So that's what statistical inference is. So yeah, first you have to make some observations of a parameter. Then you have to, in second place, you have to infer the true value of the parameter. And three, you have to estimate your level of confidence. That's when we are going to work with confidence intervals to say that in 90%, we're 95% confident that the observations and the statistical observations on this sampling can be generalized to the overall population. So yeah, the plan today is we're going to go through first the motivation. What is it important to understand statistical inference? What do you want to do it? How is it going to help us treat our oldest case and the regressions that we're going to see tomorrow? So take into consideration that actually today is more like a theoretical course. Tomorrow, in order to understand better what we're going to do tomorrow, it's not going to be exactly what we're going to do in the challenges, because we're just today we're going to try to prepare the queries and the tables which are going to help us to do tomorrow the ordinary least squares regression. So today is more like theoretical course in order to understand what we're going to do tomorrow and how can you just interpret and say something about the results that we're going to get tomorrow from the Excel data analysis added. Second, we're going to see a quick math recap with some probabilities, some distributions, some probability density functions in order to be able to attack what we're going to do today. So yeah, maybe some of you will remember quite well what you did in the past couple of weeks. If you don't worry, we're here to explain that. Third, we're going to see the sampling distribution and confidence intervals. So when you take from a larger population sample, how can you approach the statistical analysis from that sample to the global population? And that's going to be done through what we call confidence intervals. So it's quite interesting. Then we're going to see hypothesis testing with p-values. So this is something some of you maybe in product management, like in some kind of data analysis about products, maybe you wanna keep it in the scope, because the example we're gonna see today is a company develops a new feature for their app, which is gonna be we're gonna call it dark mode, and it's gonna have some impact on the screen time of the customers. So of course, when you have an app, the objective is to increase this screen time. And we're going to take a sampling. So we're going to take a small population from the total population. We're going to test what's going to be the impact of putting this dark mode into this small population in this sample. And we want to see if actually the observation that we have on that sampling group can be generalized to the overall population. So we're going to use hypothesis testing. It's quite similar as the confidence interval, but in a more practical approach. So that's quite good. We're going to see also t-test, which is something that we're going to use when we don't have a sample that is going to be large enough in order to use the central limit theorem. That's going to be something quite huge today. And finally, we're going to see Bayes inference, which is some kind of approach that you might want to use or when you have a probability of something, a prior probability, then an observation, and maybe you want to correct that kind of observation probabilities and distribution with what you thought that will have to be the prior probability. So in order to make it more clear, let's say you have a coin, which is not going to be a tricked coin. So your understanding about a coin is that half of the time, so 50% of the time, if you flip it, it's going to be either head or tails, right? So that's your prior belief. But let's say you make an experiment and you toss it 10 times in the air and you have 70% of observation that's going to be heads. We're going to see that you can adjust these observation, these 10 tries that you did with the coin with the prior probability of belief, which is going to help us correct in some kind of way this 10 tries. So that's the plan for today. I hope you're excited and you will enjoy it because it's going to be quite practical. It's a little bit it's going to be theoretical, but it's going to be quite useful, especially tomorrow when we're going to start the ordinary least squares regressions and understanding all that Excel is going to give us as information. So yeah, the motivation today. Let's recall a little bit of a business problem, right? So the problem here that we're trading this week, I guess I put it in another way so maybe you can have a better understanding, and another approach is how can you increase the customer satisfaction while maintaining a healthy order volume. So that is exactly the same as saying how can you increase the profits within a customer satisfaction approach while maintaining healthy order volume, right? So what we want to do here is optimize the customer reviews, because as you know, yesterday we saw that when you have bad reviews, it was going to create a cost for the company, which is not quite well, and it's going to decrease the profits. So you want to increase that review score. So you want to understand exactly why people is giving bad or good reviews in your company, especially here in August. So yeah, we will investigate which features impact review score the most, which could be, for example, average wait time, price, freight, distance, you name it, whatever you want. It could be anywhere, anything in all the data sets and in all the tables that we have on our oldest case. So how can we be confident about our findings? We cannot wait for the future to prove our findings right or wrong. In this case, we could, because we already have the data for 2019. We always have the data because I don't know and I don't think they have published it. But most of the time, you're going to have to treat data with you have until the present moment, and then you want to give recommendations for the future, saying that, okay, maybe this is the way the customers are behaving, the product is behaving, and you want to give something about the statistical analysis that you will do about the past time series, the past couple of years. I'll say that this analysis is going to be robust in the future. So it's going to be robust to generalization. So we're going to use for this the statistical inference analysis. So tomorrow we're going to use regressions, which is going to be the ordinary least squares to find the correlations that are going to explain review score. But we want to quantify the statistical significance of findings, and then that's going to be the statistical inference analysis that we're going to try to understand today. Okay, so we're going to start really fast with the recap for the maths module that you already saw in the past couple of weeks. So we have a little bit of probability. We're going to talk about two events, the probability of P and A, of course, the conditional probability of P, the probability of B given A. If if you remember correctly, this is going to the probability of B is going to be independent if the probability of B equal if the probability of B given A it's equal to the probability of B. You already saw also the Bayes theorem, which links actually the probability of B given A to the probability of A given B. Just keep that in mind. You don't have to remember exactly the formula. So if you want to see it and you want to learn, you can just Google it. So just keep in mind that, yeah, so the probability of B given A, the Bayes theorem links the probability of B given A to the probability of A given B. All right, it's going to be something that we're going to use for the Bayesian prior and posterior belief. We saw also the random variables, which could be something, an experiment. For example, you're going to take a person from the United States population in order to calculate its height, and maybe this person is 170 centimeters. So it has a numerical outcome of this random experiment, which is going to be the person that you're going to take from the American population. And then you're going to have a random process, which is going to be actually this repeated sequence of random experiments. And when you do it several times, when you take this x variable, this random variable x, and you do it repeatedly, so you take one person, you measure its height, you do it again, you do it again, you do it again, you enter in what we call a random process. And we know that actually there's an underlying probability distribution of x. So the distribution and the probability, what we call the probability function distribution of x is going to be defined and characterized by something that's going to be the mean and the standard deviation. So you can actually plot it. You can actually make a graph with the distribution of probability, which is going to be something depending on, of course, on the underlying probability. But for example, in normal distribution is going to be Gaussian Bell, and you can actually make a graph, but it's too complicated. So here in mathematics, in order to just characterize a probability distribution function, density function, you just use this, which is going to be mu and sigma to describe the mean and the standard deviation. So mu and sigma are called the statistics that describe the random variable x. All right. And we also saw something that's going to be one of the remarkable distribution of probability, which I have just mentioned, which is going to be the normal distribution, where you have your Gaussian Bell, and you have 95% of the observations, which are going to be between -2 standard deviation and +2 standard deviation. So a normal distribution is going to be centered around mu, which is going to be its mean, and the spread between mu and all the observations are going to be is going to be measured on most of the time in standard deviations, right? And you know that 95% of all the observations on this normal distribution are going to be situated between -2 standard deviation and +2 standard deviation, and you're going to have like 99.6 in between -3 and 3 standard deviations. We have a graph in the probably in the next slides, which is going to illustrate way better this for sure this theory. And today we're going to see something that's quite big important, because in order to generalize, how can you be sure that the standard deviation from the sampling can be close to the general standard deviation of the population? How can you just take from the sampling, this statistical analysis from the sampling, and just say, okay, how can I be sure that this actually reflects the general population distribution, for example? So for this, we're going to use a quite useful theorem, which is going to be the central limit theorem. Let's say that here you have the US population, right? So you have 300 million people here. It's going to be a mean, which is going to be called mu. And here you have the distribution of the population here. This is not at all a central normal distribution, as you can see. It could be like something like bimodal distribution, because you can think that this is going to be maybe the woman that have maybe an average that is going to be quite inferior compared to men in average height for sure. And you will also have this, which is going to be the standard deviation of the general population. So what we're trying to here to do is actually to find this mu. We're going to try to estimate this mu according to the sampling that we're going to do from here. So let's say you want to know which is going to be the American average size. All right, so you can know that. I mean, the only way to know this would be to measure all the population if you want to be for sure. But there are statistical tools like this in order to help you understand the characteristics of the general population just through sampling. So for this, we're going to take a sample X bar, which is going to be, let's say here, we're going to take a sample of 10 persons, 10 individuals that come from the population, from the American population, and we're going to calculate the average. So this X bar is the average of that sampling. So X bar is going to be X1 plus X2 plus X3 until Xn, so the 10 persons height. So because we choose a sample size of 10 here. And so it's going to be X1 till X10 divided by n, and it's just the average of the sampling, right? And we're going to put this X bar here. So for sure, it's not going to be exactly as the average population height, which is going to be mu, but actually we can see that if you do it repeatedly, this random experiment several times, it's going to be somewhere centered around mu, right? And we can also say that this distribution, which is going to be a Gaussian distribution, when you're going to put several random experiment, random sampling of this global population on this distribution, it's going to follow also a random standard deviation that can be explained and can be defined by this formula here, which is going to be 1 divided by square root of n times standard deviation, right? So this is kind of the compressed factor. So the biggest you take a sampling, the narrower is going to be your Gaussian distribution. Why is that? Because let's say, for example, you take a sampling of 300 million people. Let's say it's the total distribution, the total population of the United States. So if you take all the observations in one sample size, for sure the average they're going to find is going to be exactly the one as your mu, right? So this is like the compression factor that's going to be determined by the quantity of sampling that you take. All right. So when the independent random variables x1 to xn with common underlying probability distribution characterized by mu and sigma are added, their mean x converges toward a normal distribution as n increases, which is exactly what I just explained. It's going to be centered on the common mean of mu, which is going to be the global mean population, and the standard deviation is going to be defined by this compression factor, which is 1 divided by the square root of n times standard deviation. So in some quite easier, just to say, a mathematical way, this random variable x bar is going to become a random variable itself. It's going to be calculated, of course, as any mean, so x1 to xn divided by n. And when n is large enough for this x bar is going to be defined by a normal distribution centered around mu with a compression factor with the standard deviation defined by the standard deviation divided by a square root of n. All right? So that's the central limit theorem, and it's going to be quite useful because it's in some kind of way, how can you understand and how can you generalize sampling even if n is large enough, and we'll see exactly what it means in the next couple of slides. How can you just make this analysis about standard deviation and the mean through the general population, which is quite interesting. And we also use something that's going to be called the Z-score, okay? So let's say x is an observation derived from a random variable x that follows characterized by mu and sigma. So we do this actually because we don't, most of the time, let's say x is going to be the height measured by your sample in your, let's say we take a random sample of 1 and the x is going to be 170 centimeters, right? If you use actually the real value, you will have a scale, right? So you have something that's going to be in centimeters, is going to be something that's going to be a number where if you say, for example, okay, the standard deviation is going to be 2 or 3, if you don't have in mind exactly what you're talking about, it's going to be difficult to actually understand and interpret. So that's why I mean, I didn't create this, but most of people use the z-score in order to say, all right, so I have my 100 centimeters here, and I want to explain that in standard deviations according to the distance from the mean, all right? So that just means that actually you want to have something that's going to be expressed in standard deviations, and that is going to be a number related to the distance from this observation to the mean. So let's say we have, for example, z equals 2. That means that your observation x, it's going to be 2 standard deviations away from the mean. All right. So you can talk about anything that you want. There's not going to have a scale. It's a value that's going to be expressed in number of standard deviations above or below the mean. All right. And we can say that z can be characterized by if n is large enough, a normal distribution between 0 and 1. Why this seems quite magical, but it's not. So if you take a look at here, your random variable x bar, it's going to follow a normal distribution mu and sigma divided by square n, right? So when you just take away mu and divide by sigma divided by square root of n, you only have what is left. It's just going to be 0 and 1, because that's going to be the same here. You take away mu and then you just divide by standard deviation divided by square root of n, and then you have a z, the z-score, which is going to follow just a normal distribution centered around 0, which when a standard deviation of 1. All right, hope that's clear. All right, sampling distribution. So we're going to have an example which is going to be great. It's going to be way easier to picture and to just have an idea of what's going on with the real life example, right? So if you want to estimate the mean body height of US citizens, right? First option, you can just go through everyone's door and take the information and then just have an average, right? Because that's not going to be something that's going to be possible, and like in real life, it's going to take way too much resources and time, and it's going to be too complicated to do. So what you want to do is actually estimate the mean of the US population height here, all right? So you cannot measure everyone. As I just said, it's going to be not cost efficient for sure. So you're going to randomly select a sample of 1,000 people from the population, and you're going to measure a sample mean, which is going to be called x bar, and the sample mean of those 1,000 people that you just took from the US population is going to be 170 centimeters. And your sample standard deviation is going to be called S, and it's going to be 20 centimeters, right? So what can you say about this mean? If you had to estimate and say, all right, so according to the information that I have right now, what's maybe the best estimate, the most likely estimate for this mu, which is going to be the average height of the US population. So yeah, I guess the best estimate is going to say, we're going to have to say that it's going to be 170 centimeters from the information that we have. Here in black, you're going to have the real world, and here in red, you're going to have the actual measure. So you're sampling, so the 1,000 people that you just took in order to measure the to estimate the average height of an American citizen. So this global population is going to have a distribution, is going to have mu, which is going to be the parameter to estimate, which is going to be the average height, and it's going to have sigma, which is going to be the standard deviation of the global population. Then you just take your sample, which is going to be 1,000 people, and then you're going to have an actual measure that you can calculate and just have some statistics go through it in order to have some information. And this sampling is going to have a standard deviation is going to be called S, and a mean that's going to be called X bar. And the size N, which here is 1,000 people, right? So what we can say about this is that our best estimate of mu is going to be X bar equal to 170 centimeters, which is going to be called the law of large numbers, but you actually don't have to remember that. It's quite logical. So we're going to have to compute what we call a confidence interval around this value, all right? So yeah, what we're going to do here is actually we have a real world here in black. So a global population, here we're going to have a sampling, the actual measure, so a size of 1,000 with our standard deviation and our average X bar, which is going to be 170 centimeters. But what if, in theory, you kept doing this sampling about 1,000 people again and again and again and again? So what would be exactly the expected range of values for X bar? So the mean of means, which would be mu X bar, and standard deviation X bar, which is going to be the standard deviation of the means, would probably follow something that can be approached by the CLT, which is the central limit theorem. We actually can give a distribution of the plausible values of mu, right? So we can say, in theory, that actually this mu X bar can be approached or can be estimated, can be approached. I mean, on the contrary, this mu can be estimated or approached to this mu X bar by just saying that the standard deviation of X bar can be equal to the standard deviation divided by the square root of n, which we saw at the beginning in the central limit theorem, and that can be approached by our standard deviation of the sample size divided by square root of n. So this is what we actually are using the central limit theorem, and we're actually giving an approximation about this standard deviation of the sample and saying that it actually can be defined. We can actually describe this standard deviation divided by the compression factor. It can be an estimate about the real standard deviation of X bar, right? Of course, all this if n is large enough. So I would say that n has to be at least 30. It's going to be the number where you're going to use for the minimum sampling of the central limit theorem. If it's not 30 and it's less than 30, we're going to see what we can do in the next couple of slides, but it's going to be something that is going to be called the student test, right? So because n is large enough and the citizens are randomly selected, we can actually use the central limit theorem. The distribution of sample means X bar should follow the normal distribution, right? So this random variable X bar is going to follow the following. It's going to follow a normal distribution centered around mu, which is going to have a standard deviation with a compression factor of 1 divided by square root of n. Since we saw that with the central limit theorem, we can make an approximation saying that the standard deviation of the sample can be approximated to the real standard deviation when n is large enough. This is going to follow a normal distribution center around mu with standard deviation s divided by the compression factor square root of n. So now we have just got to replace, and we have that this will follow normal distribution with mu. The s observed in our sample in the 1,000 people that we took to a side is going to be 20, and we're going to divide that by the square root of 1,000. And we have a normal distribution center around mu with 0.63 of standard deviation, which is what you're going to see right here. So we actually know that X bar should be centered around this value mu, and we have already the standard deviation. So we already know that actually this X bar is 107 centimeters, right? So what could be the distribution of mu is the most, what distribution of mu is the most plausible, the most likely? Of course, it's going to be 170 centimeters because that's what we observed and that's what we're going to guess, right? So we can say that 170 centimeters is the maximum likelihood estimate or LME for mu. This, you already saw exactly the same graph in the past couple of math courses, I guess, but I guess it's quite important to just visualize it and remember it because this is the basic of everything. So this is really, really important that you understand. When you have a normal distribution like this, so a Gaussian belt that is centered around mu, as we saw just on the past normal distributions, you can say that if you go to the right or to the left, minus 1 standard deviation or plus 1 standard deviation, you're going to have 68% of all the observations around this, right? If you take 2 standard deviations to the left and 2 standard deviations to the right, you're going to have 95% of the observations that are going to be inside of that range, right? So inside of this curve right here, so it's kind of, you can calculate that by calculating an integral, but it's not the case here. So you just have to know that 95% of the observation is going to be around here, and 99.7% of data are within 3 standard deviations of the mean. All right. So that's really important to understand confidence intervals because you're actually seeing that if you have some observation that's going to be way more than 3 standard deviations away, the plausibility or the likelihood that this observation is actually true or legitimate, or it can be from this distribution, is quite low. So this is really important. So since we saw in the last graph, 170 centimeters is the observation and the mu that was estimated. And we have +2 and -2 standard deviations to the left and to the right, which means that we have 95% of the observations around this area, and we have a standard deviation of 0.63. So we can say that actually mu 170 centimeters plus 2 times the standard deviation, you have any observation that is within that range, it's going to be 95% confidence interval, right? It's equal to say, yeah, when you have 0.63 times 2, it's going to be upon 1.276 centimeters. And so we can say that mu is between 168.7 and 171.2 centimeters in a 95% confidence interval. All right. So these values is just going to be 170 plus 1.26 and minus 1.26. That's what it means. So how are we going to interpret this confidence interval? So what does this mean? Like we are given a 95% confidence interval. What does it represent actually realistically? So if we were to treat this process and construct many other samples, 95% of the intervals produced will actually contain the true US mean population height. All right. So let's say you have your global population here with the parameters that are going to be characterized. It's the population, and then you're going to have 1 sample, 2 samples, 3 samples, 4 samples. Let's say those samples are samples with the same n that we had before. So we take 1,000 people here, another 1,000 people here, another 1,000 people here, etc., etc. And we actually want to know if this in this confidence interval of 95%, we can say with in the 95% confidence interval that the observed mean of this sampling is going to actually be on the real mean, right? So this is going to be the real mean of the overall US population, I guess, on height. And this is going to be your sample. 1, this is going to be your sample 2, this is going to be sample 3, 4, 5, 6, 7, etc. What you can say is that 95% of the time, the sampling that you will make here, whatever, here, you're going to have the true average value of the global population in your 95% confidence interval. 5 out of 100 times, so 5% of the time, you're going to have a wrong prediction. So 5% of the time, you're going to have something that's actually not going to take inside the true mean of the average population, even with a 95% confidence interval. That's what it means. So we're actually 95% confident that 168.7 and 171.2 captures the true mean height of the US population. So yeah, here is we use a little bit of Python just to visualize a little bit what is going on. So you don't have to understand actually the code. What we're saying is we're creating this normal distribution, which is going to have an average of 170 and standard deviation of 0.63, and we actually want to calculate the confidence interval just to check the facts that everything that we've said until now, right? So we take this 170 and we take 2 times 0.63, which is going to be 1.26. So here you're going to have 171.26. Here you have 168.7, which is going to be 170 minus 2 times 0.63. And then you ask this program, this function, to just calculate the confidence interval. And as we know, it's going to be 95% confidence interval, because we know that on the 2 times standard deviation spread, you're going to have 95% of your confidence interval. So yeah, just to talk a little bit about vocabulary. So usual English names for confidence intervals. So this is the International Climate Change Conference that actually uses this in the reports just to see, but they actually don't tell it's going to be 68, 95% confidence interval, 95. They just use some human vocabulary and they actually associate it with the confidence interval, right? So when they say something's likely, it's on 68%, very likely it's 90%, extremely likely 95%, virtually certain at 9.7%. And actually, just for the anecdote, when you want to prove threshold in theoretical physics of something, you can use a 5 sigma spread in order to use that as a proof. And if your findings enter in that range, you can actually consider it as a theoretical physics proof. Here we have some graph about people perception, about the vocabulary used to define a probabilistic event. So people associate the almost certainty sentence or vocabulary to something that's going to be around 95%, high likely about 9%. We're not going to go through all of them, but it's just something that you can check or take a look, to have just an idea about what people and perception of people is about these sentences and these probabilistic sentences, and see how you can use it intelligently in your presentations or in your pitches, right? So yeah, almost no chance, it's 5%, highly unlikely, it's going to be around 7%, etc., etc., etc. All right, so we actually said in all the exercises that n has to be large enough for the CLT, right? But so what does it mean? Like, if n actually is superior and bigger than 30, then you can apply this CLT, central limit theorem. And we can actually approach, and sample STDS can be used in approximation for the true population standard deviation in the Z statistic, which is what we did just before. If n is superior to 10 and observations are non-skewed and without outliers, CLT applies. This is going to be a little bit difficult for you to maybe to check. So I guess just take the 30 observations for most of the time. And if global population is known to be normally distributed, CLT always applies with arbitrary small n. So yeah, if you already know that the population where you're taking the sample has a normal distribution, you can also apply the CLT. So it doesn't, it could be for n equal to 10, 9, and 15, whatever, under 30. But you have to be sure that actually the distribution of the global population follows the normal distribution, which is rarely the case and unlikely to prove, but quite difficult to prove. But if you're going in some kind of theoretical way, you can actually use this. So what happens? What can you do when n is small enough to consider each joint? So what happens if n is small enough? And we want to consider that each joint is independent and without replacement. So actually, when you make this sampling for the CLT, each of the draw has to be independent, right? For this, you can say that n and the sampling is going to be independent if n is strictly inferior to 10% of the global population size. So what does this mean? This means that, for example, let's take a deck card which has 52 cards, 54, 52, something like that, and you want to take a sample. If you take 1, 2, 3, 4 cards, it's going to be considered independent if you take less than 10% of all the population, which in this case is going to be around 5 cards, right? If you take more than 5 cards, it's not going to be considered independent, and you won't be able to apply this CLT. So what you want to do is maybe take a sampling, then put it inside again into the deck, reshuffle, and take again another sample. That's what you want to do. If you want to take sampling, that's going to be maybe more than 10%. So if you want to take a sample of 10 cards on your deck of cards that you have 54 cards, what you want to do is actually maybe take 5 or take 3 or 2 and then just put it back, and then take 2 and put it back, reshuffle, take 2 and put it back and reshuffle, in order to have the statistical requirements to apply the CLT. All right, so let's pass to the next part, which is going to be hypothesis testing. So here we have a clear example. So let's suppose we're going to be the product manager of a social network mobile app, right? And let's say that our users are going to spend around an average. So we know mu, which is going to be 300 seconds per session. And they have a standard deviation around 50 seconds, all right? So we have the intuition that if you change the background color of your application to something that's going to be a more like dark mode, you would increase the time spent per session, which is your objective, but because you always want users to take and participate and consume more time of the application, right? So how can you be sure that you can test this hypothesis in some kind of statistical rigorous way in order to convince the CTO to roll out the new feature? So we're going to have to check that. We're going to do something that's going to be called A/B test, all right? So it's going to be some kind of experimental design, and we're going to do it following the following steps. So the first of all, of course, you have to develop the corresponding feature in dark mode. If not, you cannot test it. You're not going to have any information. So you cannot test it if you don't have the feature. Second of all, you want to create 2 groups. So you're going to have to create a control group and a treatment group. So control group, it's going to be a group that's going to be somewhere where you're not going to deploy your new feature, and the treatment group is the group where you want to deploy the new feature. All right. You can randomly assign, for example, 100 users to the treatment group in order to test the new feature. You're going to deploy this dark mode on the treatment group only, and then you're going to have to analyze the statistical behavior of this treatment group to see if actually there's a difference between them and the normal group. Let's say we actually did all these steps and we actually find that there is an increase in the sample mean of X bar, so in the treatment group where we actually took this dot feature into the application, and we see that there's an X bar corresponding to 310 seconds. So how can we be sure that this observation is going to be something that can be generalized to the entire population and the entire user base. So we're going to use something that's going to be called hypothesis testing. What we want to do is actually choose, first of all, what's going to be called a null hypothesis. So the null hypothesis is going to be H0, which corresponds to dark mode doesn't change anything. It changes nothing, right? And we're going to have an hypothesis A, which is going to be dark mode is better. Before starting the experiment, and this is important to do, you have to establish a significance level. A significance level, it's going to be according to the risk that you're willing to take from the error, right? From the what if I'm mistaken or whatever. So you're going to accept some kind of significance level. Is going to be a threshold that you're going to establish before the experiment. And you're going to say, okay, most of the time people take 5%. It's what's more used, but it's going to be depending on the problem. I mean, like if you're taking a COVID vaccine analysis or something, you want to be more strict on the significance level. Maybe you want to take it to 2%. I don't know. So this is something you want to discuss with the team before, and you want to create this significance level. Once you have established your significance level, here it's going to be 5%. We're going to take this, the global population. We're going to see what the mean is, the standard deviation of the total user base. We take a sampling on the treatment group, and we measure the sample mean screen time, which we already know that x bar is equal to 310 seconds. So we might think that actually the dark feature is improving in some kind of way in the app, and people are willing to stay more because there's this new dark feature. So we want to calculate the probability of x bar, so of having the users staying more than 310 seconds or more, given that the dark mode changes nothing. So is it likely to have this screen time observed in the distribution of the user base, knowing that this dark mode is not going to change anything? And that value, that numerical value that we're going to calculate here is going to be called the p-value. So if you have a p-value that's going to be under your significance level, so it's going to be under this threshold of 0.05%, if I mean 5%, which is going to be equal to 0.05, you can actually reject the null hypothesis. And you can say that it's really unlikely that you can observe these 310 seconds on the user, knowing that the dark mode changes nothing. So there's got to be something that implied that the product actually got better, right? So it's not a normal observation if the dark mode didn't change anything. So, and if you observe something that's going to be higher than the significance level, you can say that it's likely that you can observe this in the user-based distribution. So you don't want to actually accept the, you don't want to reject the null hypothesis, and you might accept it, saying that actually the mode doesn't change anything. So what if you want to reject this null hypothesis, you actually want to HO will be actually false, right? So if HO, which means the null hypothesis, is actually false, it means that the dark mode is good. So you're going to be here. You're going to be correct. If you fail to reject the null hypothesis and you say, okay, it doesn't change anything, so you didn't want to implement it because it's not improving anything, you want to be around here. But actually, you can have some kind of error, because as you're saying, you're using the 95% confidence interval, so you're using a significance level of 5%, which means that actually there's some kind of 5% probability that actually the observation here, I mean, the tolerance is not the probability of this, but I mean, the tolerance of this being here is 5%, but you can actually be, you can actually have an observation that's maybe going to be an outlier or something, or that's going to be plausible or likely in this distribution. And if that's the case, I mean, you can say that even if the significance level it's inferior to the threshold that you have, you can have what we can call a type 1 error if you reject the null hypothesis and you go dark, but actually dark mode didn't change anything. Or you can fail to reject the null hypothesis, saying that dark mode is better, but actually dark mode did change something, right? So yeah, this is mostly what I just said. So yeah, you want to test your hypothesis, you create your new hypothesis, you create an alternative hypothesis saying, okay, I want to say that mu is going to be superior to 300. I want to choose a significance level, which is going to be 5% here. You're going to suppose that the new hypothesis is true, and then you want to compute the probability of observing that sample on if the new hypothesis was true, all right? And that's why you're going to calculate your p-value, and then you're going to have a value that's going to be associated and compared to the significance level that you define, and then you're going to reject or accept the null hypothesis. So how can we calculate this p-value? So since n is going to be large enough because we have 100 here, we can use the central limit theorem once again. So the distribution of the sample mean x bar should follow the normal distribution, right? So supposing the null hypothesis is true, which means that the dark mode is not going to is useful, it's not going to change anything, then we know that our distribution or random sample here it's going to follow normal distribution with it's going to be centered around 300, and it's going to have a standard deviation about 50 divided by the narrowing, the compressing factor is going to be 1 divided by square root of your n, which here is 100. And so we're here, center around 300. This is going to be our sigma, and we're going to calculate this p-value, which means if it's likely, what's the probability of the probability of having 310 x bar superior to 310 is knowing that the null hypothesis it means that the dark mode doesn't change anything. When actually, just to explain a little bit, 2 seconds, saying that actually you're assuming that H0 is true means that you're actually taking the mean of the standard of the group without changing anything. So you're taking the mean of the global population because it's actually the group where it wasn't tested. That's what it means here. And you want to use what's called a standard Z table to calculate the p-value. So here we're going to use something with Python in order to calculate this, but you can use what is called an ABAC table, which will allow you, we will show you how to calculate it, but there are common tables on the internet. You can just check knowing which is going to be the p-value associated with a normal distribution of this characteristics. And we find out that actually our p-value is going to be 0.02, right? So it's going to be 2%, which is inferior to the 5% of threshold that we established, so we can reject the null hypothesis. Just what I said, p-value is going to be inferior to 0.05, we can safely reject the null hypothesis. Dark mode is a real plus. So yeah, here I was just talking about this, about the type of errors that you can have when we actually you have something that's going to be in the significance level that you want, but you can actually make a type 1 or type 2 errors, all right? So how can you choose the significance level? So this level is usually in initial clinical trials. The 0.05 is usually in the first trials of your hypothesis, right? You want to never change your significance level afterwards, because if you do this, it's kind of cheating. You know, like you have it could be 5. If you find your p-value is going to be 5.5%, you can say, oh, all right, so it's not that far away from 5, so I guess we can take it. No, you establish a threshold and then you just stick to it until the end in order to be sure that actually it's going to be a reliable statistical experiment. And you can choose your alpha depending on your susceptibility to type on 1 and 2 errors. So this and this errors. So it depends on the problematic. Do you want to really accept a vaccine that changes nothing? I mean, you can assume that the vaccine changes nothing, but actually it does. So what's going to be the effect on people, on population? You want to reject the vaccine. So you want to say, okay, the vaccine actually is not, it changes nothing. So you reject, but the vaccine could be actually beneficial to the population. So depending on the problematic that you have, you're gonna be more strict or less strict on the type 1 or 2 type errors that you can have, depending on the significance level that you can choose. All right, and we're gonna part to t-test. We still have 2 parts, which is gonna be t-test and Bayesian prior and posterior likelihood. So for the t-test, which is going to be something that can be used when n is not large enough to use the CLT. So yeah, we were saying that, all right, we can generalize, we can use, and we can use this approach and say that it follows a normal distribution with these parameters if n is large enough. But what if it is not? So what if our sample n is not large enough? We don't know the true population of sigma. So it's quite difficult because it cannot be approximated by the normal distribution 0, 1, and it cannot be computed without knowing the true population. You cannot actually estimate mu, and you cannot estimate the sigma of the population without knowing the sigma of the population. You cannot make the approach of S through sigma, right? So that's why statisticians came up with something that's going to be called the test statistic. So the test statistic, it's going to be something that can approach anything, even if it's a sampling of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it doesn't matter. It means that you can approach this through a test statistic, saying that you can approach this, what we have, which is going to be your X bar, the average, the mean of your sampling minus the true meaning of the population divided by your compression factor, which is going to be S divided by square root of n. And it will follow not a normal distribution of 0, 1, as it did with the Z, but it will also it will follow a distribution of T n minus 1, 0, 1. And this is called the student T distribution. And this is what we're going to call the degree of liberty, right? So it's actually quite similar, but you will have one more parameter, which is going to be this n minus 1. So yeah, so just to be clear, you can actually approach also sampling that are superior to 30, 20, a million, whatever, with this T study. Why do people prefer to use the normal distribution and the central limit theorem? It's just easier because it has less factors. It doesn't have the degree of freedom, so it's easier to estimate and to use. So if you want to have fun and maybe use this to estimate everything, you can, but it's going to be more complicated because the central limit theorem is way easier because you don't have as many estimates and as many parameters to check your distribution. All right, so everything applies as before, replacing just your normal distribution with the distribution. Instead of using z-test, you're going to use t-test. And you can compute this confidence interval of measurement. And you can have your test hypothesis, compute the p-value, and you can have your significance level of alpha that you're going to be determining and decide. It still requires independent and random sampling, so as I told, just to recall, you can take less than 10%. If it's more, you want to report it, reshuffle, and retake your sampling. So what does this look like? This student T distribution. So this T distribution is going to have this, which is going to be called eta, I guess, mu and sigma, which is quite similar to the normal distribution. It just added one more parameter, which is going to be the degree of freedom, and it's going to be accessible via the T table. What we can see is actually that the T distribution has what we can call fatter tails than the N distribution. So the T distribution is going to actually can be described as a normal distribution when the degree of freedom is large enough, which is what we already saw in the past couple of slides. So this degree of freedom is n minus 1. So I guess if you have a degree of freedom of 30, 35, 40, or something like that, even 31, you can approach it as a normal distribution. So here, the black curve, it's going to be normal distribution. because the black curve corresponds to a degree of freedom where the degree of freedom it's tending versus plus infinite, so it can be approached as a normal distribution. And the other ones, as you can see, have favor tails. What does it mean? It means that you're less certain of how the distribution of the people are going to be. So since you're less certain, you want to take into consideration a bigger area, so you can have more spread and be sure that it's going to be between your confidence intervals. This is the table that people use in order to check what's going to be inside of using the T distribution. So this table gives actually the value of the distribution of n degrees of freedom. So for example, if you wanted to measure 14 people at random and found a mean height that has a value of t-score of 3, then 14 people, it would mean that the degree of freedom is going to be 14 minus 1, it's going to be 13. So we can just scroll it here. It has a degree of freedom of 3, so we can go back here. Here we have our degree of t-score, and we can say that we have just measured is 99.5 improbable, right? So that's how you read this kind of table. That's how you can see actually how unlikely it is to have these observations for your confidence intervals and for your testing. So yeah, so here you have some kind of central limit theorem generalized, so you can check it out with the T distribution, the N distribution, and if you want to check a little bit more information, you can also see the best correction to try to understand where does the degree of freedom comes from. Okay, finally, we're going to end with the Bayesian interpretations. This is quite logical. It's just so you have an idea and you have some intuition about this. Maybe one day you'll have to treat probabilistic cases and business cases that can be approached with this. So, yeah. Let's sample a coin by flipping it n times to measure its fairness. So the probability of having a distribution which is going to follow the distribution characterized by its mean and its standard deviation of landing on its head. So let's say this coin is going to be fair, which means like before doing the experiment, we already know that when you toss a coin, you have 50% chances of having tail or heads, right? But so prior to the experiment, we may have an opinion about what the coin fairness is, right? And the initial belief is called the prior belief, the prior probability P of H, H being the heads random experiment, right? If we have no opinion, we model the probability of this random experience as a new uniform distribution over 0, 1. So we're going to cause we're going to toss the coin 10 times, and we're going to find the sample mean is going to be 0.7. And there's going to be a deviation, a standard deviation of S. So what is our new best guess for H after having seen the new data? So having what's the probability of having a head knowing this data? So what's the posterior probability? So yeah, in the absence of the more prior beliefs, we can only rely on observation, right? So our most likely estimate is going to be 0.7 for the average, the maximum likelihood estimate, which is what we observe when we just toss the coin 10 times. Our new best guess posterior proba of the coin fairness, which is P, probability of H given data, is equal to something that's going to follow a normal distribution of center around 0.7 with the standard deviation of sigma divided by the compression factor square root of n, which is going to be normal distribution about 0.7, 0.1. So here we can see that the central limit theorem actually tells us what is the most likely distribution from which such mean of 0.7 have been drawn. So this is called the likelihood of observing the data, all right? So here, if you have no idea what the prior probability is, we're just going to create something that's going to be a uniform distribution, which you can see here. So it's going to be something that's going to be as likely at 0 than 1. So that's what we call a uniform distribution. Here you have your tossing, so which is going to be centered around 0.7, and here you are going to have your MLE, which is your maximal likelihood estimate. All right. Now let's guess, and let's say that you have a prior belief. So you do know that a coin that's going to be fair has to be 50% of the time tails and 50% of the time head. So the extreme values close to 0 and 1 seem very unlikely to us. So we can see visually that it's unlikely that the distribution is going to be more skewed, or is going to be more centered around values that are close to 0 or 1, because we know that the coin is fair, and we know that our prior belief is that it's going to be around 0.5. So we'll actually model our prior belief, saying that it's going to be centered around 0.5, and it is going to have a standard deviation about 0.3. So what is going to be our now guess for our sample or random variable after having seen this new data of P, a probability of H of heads given this data? So what you really want to do is actually adjust the observation. So you know that there was some probability about 0.7 having heads, knowing that actually that's not quite real. So you want to adjust it. You want to adjust it because you have a prior belief. So you want to actually bring it more into the realistic perspective because you have some information previously to the experiment. And we got something like this, right? So what is this? Here in black, we're actually drawing what's going to be a prior probability, right? So it's going to be a distribution, it's going to be centered around 0.5, it's going to have 0.3 standard deviation, and it's going to be distributed like this. You had your likelihood, which is here, which is the observations we did on our experiment. So we have your maximal likelihood estimate, which is going to be 0.7 because we tossed the coin 10 times and 7 times it was head. So the red one is going to be the experiment one. And then you want to actually create or adjust or correct a little bit this likelihood, this MLE, by saying that your posterior probability of the probability of having heads observing the data updated with the prior beliefs is going to be somewhere around 0.5 and 0.7, which here is going to be, I don't know, let's say 0.6. I don't know what exactly is here, but it's going to be something around here, and it's going to be called the max a posteriori estimate. So what you don't have to actually learn the formula by heart, but you have an intuition about how it works. You can always Google it and look for it. But what you want to see is that actually your posterior belief is proportional to the prior belief times the likelihood. So you want to use base to update your prior belief into a posterior belief in order to correct. This is way used, for example, in polls for political matters. I don't know, in the United States, for example. So knowing which were the trends last year, or how popular was a candidate last year. If you make a new poll and just a new sampling about the perception of people for this candidate, you want to also update it through your past prior belief, which is going to be maybe giving more information to your statistical analysis and giving you a more like close to reality perspective. So that's going to be all for me. You can check some of the bibliography if you want to have more information about Bayesian, how you adapt your probabilities, Bayesian inference or parameter estimation. If you want to have some more statistics, background exercises and videos, this is the Khan Academy. It's great. Or maybe if you want to learn a little bit more about causal inference, you can go to this link right here. Actually, just to end today, we're going to be creating through some queries on the Excel Power Query tool. We're going to have to create what we're going to use tomorrow to create models of the linear regression, right? Today is going to be more of getting used with technical use of the tool of Excel, you're going to have to make either pivot tables or just merges using the query system, the Power Query system. I recommend that you use maybe one to understand how you make your pivot tables, but the essence of this is that you actually learn to make queries because it's way more practical. You're going to be able to export these queries into Power BI, whereas if you have a TCD, maybe it's not going to be as exportable, as easy exportable as these queries. So yeah, these queries are going to be integrated because, as you know, Power BI has the same Power Query operator that's going to be like the main engine in it, and it's going to be way easier to maybe make your inference statistics in Excel, and maybe when you're sure that these are going to be the columns that you want to use because this is going to be what determines and what explains your target, you want to export it to Power BI and then just represent and make some hypotheses and make some dashboards that are going to be quite visual for your CEO. So today the challenges are not going to be exactly around statistical inference, but tomorrow what you're going to start doing with Excel, with the data analysis toolpack in Excel, you're going to have to analyze some of these features, and you're going to see that you're going to have the p-values, the t-values, the confidence interval. You're going to have a lot of this information, and it's important that you understand and that you just did this today in order to understand what Excel is giving you tomorrow. So yeah, I hope you had a good lecture, and good luck today for the challenges, and good luck.